Our immediate application of this model is to vectors. And I assume that you're familiar with the basic idea of a vector, but let's be kind of specific here. If we have a vector that we'll call R, that would be a capital R in this case, with an arrow over the top of it, the arrow indicating that this is a vector quantity, you know a vector has a magnitude and a direction. The direction of this vector can be specified by the angle, and let's call that angle theta, again measured from the positive x-axis around to the segment that represents the vector. And its magnitude could be written as magnitude of r. That's kind of a double absolute value sign. In mathematics that would be called a norm sign. So the absolute value of r, the magnitude of r, and if we're talking about the magnitude of a vector, we can just refer to the magnitude as the letter that stands for the vector without the arrow over it. So the magnitude of r could just be represented by plain old r. Now this vector has components. It has an x component and a y component. The x component is obtained by, well, let's do the y component because I kind of, well, you see. The y component, we simply project over to the y-axis and take a vector that runs from the origin down to that point. Now I've offset the vector a little bit because I don't want it running through my indication of the angle, but ry could be considered to be a vector, okay, a vector whose length is equal to this distance. And of course you know from the circular definition that that's just going to be equal to the magnitude of r times the sine of theta, because this is just the y coordinate that we get when we make this arrow, okay? Rx is the x component of the vector. I interrupted the projection line with my labeling here, which is why I decided to start with the y. But the Rx vector just runs from here to here, and its magnitude is clearly then going to be equal to the magnitude of r times the cosine of theta. So we can write this here. Now I've only used kind of a single absolute value sign instead of the double absolute value sign here. They're kind of interchangeable unless you want to get really technical. The magnitude of Rx is the magnitude of r times the cosine of theta. The magnitude of Ry is equal to the and what I wrote here makes no sense. I'm going to stop for a second and fix this. Okay, I've made a couple of repairs here. Let me back up to what I said over here. I'm not going to regard, it's perfectly okay to regard Rx as a vector from here to here, Ry as a vector from here to here. This would be the vector that represents the component of r in the x direction. This could be the component of the vector component of r in the y direction. However, in defining these things, the formulas don't make sense because cosine theta and sine theta can both be positive or negative. When I put absolute value signs around all these things, everything is positive. That just clearly isn't so. So let's let that be a lesson. When you write things down, think about what you're writing. Don't think about them later and have to correct them. Okay, I'm going to regard Rx as simply a signed number. So this is like an arrow on the number line. We're not going to regard it as a vector. And this is going to be a number on the number line. In this case, Rx is going to be a positive number. Ry is going to be a negative number. So Rx is going to be the scalar component of the vector r. Ry is going to be the scalar component in the y direction of the vector r. Rx the scalar component in the x direction. Ry the scalar component in the y direction. So now we can write Rx equals r cosine theta. Remember that r is just the magnitude of r. The magnitude of r is going to be a positive number, so r is a positive number. However, when that positive number is multiplied by a cosine or a sine, it can become positive or negative. So Rx can be positive or negative, Ry can be positive or negative. Again, in this case, Rx would be positive, Ry would be negative. Now, by the Pythagorean theorem, we can see that Rx is the length of the side of a right triangle, and Ry is the length of another side of a right triangle whose hypotenuse has magnitude of r. So that the square of this side plus the square of this side has to equal the square of this side, so that Rx squared plus Ry squared has to equal r squared. Now, we haven't defined the tangent, and I'm assuming that everybody in a university physics course has had sufficient trigonometry to understand this. Didn't define the tangent up here, but the tangent is defined as the sine divided by the cosine. That would be the y divided by the x. So for any angle, if you divide the y coordinate by the x coordinate, you get the tangent. The tangent has the sometimes inconvenient property that the tangent of an angle in this quadrant, well, the tangent doesn't distinguish between the first and third quadrant or between the second and fourth quadrant. And that's something you should be familiar with. I'm not going to go into a lot of explanation on that, although if you want it, submit a question. I'll be glad to answer it. Okay, so the result of that is that the tangent of theta is the sine divided by the cosine, which is the y-coordinate divided by the x-coordinate, so that the angle will be the inverse tangent of the y-coordinate over the x-coordinate. But to distinguish between first and third quadrant or between second and fourth quadrant, we add to the rule that we add 180 degrees if Rx is less than 0. Now again, I could go more deeply into that. The inverse tangent is going to be between negative pi over 2 and pi over 2. So if you want an angle between here and here, you're going to have to add the 180 degrees or pi radians. These four relationships completely define the vector and its components in terms of the sines and cosines. If you know the vector, the magnitude and angle of the vector, you can find its components. If you know its components, you can find its magnitude and its angle. Now there's more here in the introductory problem set 5, and I'll make sure that's clear in the assignment. I'll give you a link to that. There's a set of problems that I ask people to work through that pretty much nails the whole basic concept of vectors. Now, it doesn't get into cross products and dot products and so forth, so we'll talk about that a little bit. And I just made a note here. The signs are automatic. If we use the circular definition, we don't have to worry about whether a vector is going to the right or the left. If we get the angle right, the positives and negatives are going to take care of themselves.